Hello, welcome to the course page on digital signal processing. Our discussion is on frequency analysis techniques, and we have used different frequency domain analysis techniques. One is a Fourier series and the other is a Fourier transform, discrete time Fourier transform, discrete time Fourier series. And these are the methods that we discussed in the last few classes. Now, where we will use these techniques, if your signal is a time domain, if it is continuous in time and it is aperiodic, we will use a Fourier transform, and its frequency domain becomes a continuous and aperiodic. And if the signal is continuous in time and it is periodic, then we'll get a discrete spectrum in the frequency domain, and the signal is an aperiodic. And again, the next case is with the discrete time, when the signal is discrete in time and it is aperiodic, and we'll use a technique known as a discrete time Fourier transform for an aperiodic signal, and we'll get a frequency domain analysis will be continuous in the frequency and it is periodic in nature. And again, and the last case is a discrete time Fourier series. And in case of a discrete time Fourier series, if the signal is discrete in time and it is periodic, and you will get a frequency domain analysis contains discrete and it is periodic. And again, if you want to relate or if you want to remember this thing, then you can use this notation that if the signal is continuous in time, then its frequency in frequency domain, if it is continuous, then in frequency domain it becomes an aperiodic. And if the signal is aperiodic in the time period or in the time domain, then it becomes a continuous. And if the if the signal is periodic in time domain, then you'll get a discrete spectrum in the frequency domain. For every periodic signal, we'll get a discrete spectrum. For every aperiodic signal, we'll get a continuous spectrum. And the reverse case is also same. And here it is in frequency domain, it is aperiodic. So we'll get a continuous spectrum in the time domain. And here, if it is in the discrete time case, then it is discrete. So we'll get a periodic signal. Here again it's discrete and we'll get a periodic signal. For every discrete time signal, we'll get a periodic signal in the frequency domain. And for an aperiodic signal, and if the time domain is aperiodic, then we'll get a continuous spectrum. If the time domain is periodic, then we'll get a discrete spectrum. So this is the relationship, and you can easily understand the concept behind or where we will use these techniques is. So we can sum up these things. A continuous time will get an aperiodic spectrum. For discrete time, we'll get a periodic spectrum. And for a periodic signal, we'll get a discrete spectrum. If the signal is periodic signal, we'll get a discrete spectrum. If the signal is aperiodic, then we'll get a continuous spectrum. That's the relationship between these two things. Okay, so that's fine. And in this case, I have illustrated the things, and here the signal is in continuous time. The signal is continuous time and it is periodic. And here, see here, this signal is periodic and it is having, and from this place to this place, up to this. Okay, yeah, up to this. This is the period. Okay, to this period, we can have a from this place to this place. This is, am I right? No, I'm sorry. Yeah, from this 0 to TP is the period, time period, and we can have this area. So again, if you can see here, this is the case with a its frequency spectra contains an aperiodic signal. Here it's an aperiodic. There is no periodicity here. It is not repeating. And also, moreover, since the signal is continuous, then we'll get a discrete spectrum. Okay, sorry, it's a discrete spectrum. We obtained a discrete spectrum because since it is a periodic signal, and since the signal is continuous, we'll get an aperiodic signal. Okay, yeah, I think that's the case. Continuous time, we'll get an aperiodic spectrum. For a periodic signal, we'll get a discrete spectrum, right? So that's the case with this. Again, in the second case, the signal is continuous, and here the signal is continuous, but it's this is continuous signal, but the signal is aperiodic, so we'll get a continuous spectrum, and also it is aperiodic. Since the signal is continuous, we will get an continuous an aperiodic spectrum, and since the signal is aperiodic, we'll get a continuous spectrum. Okay, that's the case with Fourier series and Fourier transforms are the two techniques that we normally used with these. Now with the discrete time, here we have a discrete spectrum and it is periodic, and we'll get the Fourier series, and we'll get a discrete spectrum, and again the signal is periodic. Okay, here it is periodic. The same signal is repeats. The same signal is repeats from here to this, and again it's repeating here. See here, from this place to, sorry, from this place to this place, again in between all these points, see, it is repeating from 0 to 9. So that's why we call it as a discrete in time, and it is periodic. And what about this case? In this case, here it is a signal is discrete and it is aperiodic, and we'll use a discrete time Fourier transform, DTFT, but we'll get a continuous spectrum here, and we'll use these equations. Remember these equations I have discussed in the class. These are the equations to find the discrete for analysis of and the synthesis and analysis equation of Fourier transform and Fourier series.